everyone! Welcome to part 2 of chapter 17. Today we are going to talk about titrations. So we're going to start off with what titrations are, which you should have covered in Chem 1, but this will be kind of a quick review. And then we're going to look at the calculations associated with strong acid and strong base titrations. Weak acid and weak base titrations will be covered in the next lecture. So we've learned about neutralization reactions before, and this is when an acid reacts with a base to produce salt and water. But now we've learned about different types of acids and different types of bases. We know that there are strong acids and weak acids, and strong bases and weak bases. So a neutralization reaction is only going to occur between a strong acid and a strong base. That will give us a solution with a neutral pH at the end of 7. This is because the salt that's being produced doesn't have any ions that have any acidic or basic properties, right? The sodium is going to be the cation of a strong base, right? Sodium hydroxide. And the anion, chlorine, is going to be the anion of a strong acid, hydrochloric acid, which means that both sodium and chlorine have no acidic or basic properties. So after the reaction happens, all we have is sodium chloride and water. We have salt water, which has a pH of 7. So again, we must have a strong acid and a strong base, and they have to be mixed in their mole ratios that are specified in the balanced chemical equation. So for every 1 mole of hydrochloric acid, we need to have 1 mole of sodium hydroxide. If these were, say we were using, sulfuric acid, that would need to react with 2 moles of sodium hydroxide, but it would still result in a neutralization reaction. So titrations are an application of neutralization reactions, and they're usually used to determine the unknown concentration of either an acid or a base. So we'll always know the concentration of one of them, we'll know the volume of both, and we'll typically be trying to figure out the molarity of the other. So in this particular example, we would know the concentration of our sodium hydroxide. This is usually going to be called our standard solution because we know the concentration. And then our nitric acid is the one that we don't know, right? So that would be our analyte. So the titrant, right, which is our standard usually, but the titrant is what goes in the burette. And if you're not familiar with the burette, which hopefully you are, but the burette is this piece of glassware here. It is a very long, skinny piece of glassware, and it's quite fragile, so when we use it in lab, please be careful. But the reason that it's so long and skinny is that it gives us a really accurate measurement of volume because it's so narrow. And when we read it, there's going to be a 0 at the top, and there's typically going to be a 50 at the bottom, and we read the volume going down. So this is a little bit different than other pieces of glassware, like a graduated cylinder. We typically read the volume on those going up. But this is because as the reaction proceeds, you are, showing, you can calculate how much you've added. This here is called the stopcock. That is what controls, the addition of the acid or the base. You just spin the stopcock, and if it's completely open, it will come through quite quickly. Right now, it looks like our titrant is coming through dropwise. At the bottom in this Erlenmeyer flask, we have our analyte. And that would, again, be the one that we are trying to figure out something about. Usually we're trying to find out the molarity. And in the last example, like I said, this was sodium hydroxide up in the burette and hydrochloric acid down in the bottom. In Chem 1, we did a titration where we used sodium hydroxide to titrate against acetic acid and figure out the concentration of acetic acid. So again, if you had an acid of unknown concentration, you would add base with a known concentration until it has been neutralized. Okay, so our goal is to have exactly the amount of moles of acid equal the moles of base. Okay, and then if our moles of acid have exactly equaled our moles of base, that means they have reacted in exactly stoichiometric amounts, and all we will have left over is water and some salt that doesn't have any acidic or basic properties. So when this happens, when the moles of acid are equal to the moles of base, we call that the equivalence point, right? Because we have, equivalent amounts of acid and base that have been added. You may hear the term endpoint. And in a lot of cases, and in Chem 1, we use those kind of interchangeably. We say that, the equivalence point and the endpoint are more or less the same thing. In this class, I want to make the distinction between them. Equivalence point is where the moles of acid are equal to the moles of base. That is what should be the end of our titration. The endpoint is the point at which the indicator changes colors. So it's really important to pick an indicator that has a pKa that's close to our equivalence point, our pH, where our moles of acid would equal our moles of base. So the goal would be to make the endpoint and the equivalence point the same, so that our indicator changes color at the same time our reaction is actually done, right? Because otherwise, if we don't have an indicator in there, where there's no way to tell, right? There's no way to see visually that our moles of acid are equal to moles of base. If you think about the titrations we've done in the past, we're looking for that very faint pink endpoint. We're looking for the point, that we've added, enough of our base that our phenolphthalein that's clear in acidic solutions turns a very, very, very faint pink, which means that it's ever so slightly basic, right? So we've actually gone a little bit past the equivalence point, because typically we want, pH maybe 7 of a strong acid, strong base titration. And if we've gone, if we have it slightly pink, that's going to be slightly basic, which is why we want it as faintly pink as possible. So again, the endpoint and the equivalence point are not always the same, but they should be. Equivalence point is the actual end to your titration, where your moles of acid are equal to your moles of base. The end point is where the indicator changes color. And we're going to talk more about how to choose a good indicator at the end of the next lecture. So again, an indicator is used to determine when the acid has been neutralized in a titration. So it's really important to know the approximate pH at which that will happen, because indicators change color at a very specific pH, and there'll be one color in an acid and one color in a base, just like we were working with methyl orange, right? And it went from red to yellow. Without an indicator, like I said, you wouldn't be able to know when your titration should stop, because your base is clear liquid, your acid is clear liquid. You add two clear liquids together and you're going to still get a clear liquid. Like nothing visually is happening. So that's why we add the indicator, so that we can see that color change to tell us when to stop. The other way that you can do this is you can use a pH meter, and you can actually monitor the pH of the titration. And this is what we're going to do in the titration of a diprotic acid lab, because you'll see this curve, which we're going to talk about today. And then you can figure out the endpoint of the equivalence point of your titration, because it will be at the inflection point of the curve. So that's how you would use the pH meter. And we're going to talk a lot about titration curves in this lecture and the next. So again, here's what it would look like with an indicator. So at the beginning of your titration, if you have base in your burette, and you have acid down in your Erlenmeyer flask, and you add some phenolphthalein, you're not going to see a color change in your Erlenmeyer flask, because your phenolphthalein is clear in acidic solutions. But as you start to add base, you start to see pink, right? And then you'll add a couple drops and you swirl, and you add a couple drops and you swirl, right? And that pink color will go away, because there is still more acid in your flask than there is base. But once you have more base, then your solution will turn pink, because your phenolphthalein, right, your indicator, is pink in basic solutions. Just as like a heads up, I know this is the image that they give you. If your solution is that color, that is too dark. You're actually, if you look, this faint pink, you're looking for more of that color throughout the Erlenmeyer flask. This would be, this really dark pink that you're seeing here, that would be too far. You've gone too far past. Maybe only a drop or two, but you have gone past the equivalence point. So to sum up, in an acid-base titration, we normally have one, unknown concentration. This should say our known concentration, our titrant, is slowly added to a solution of unknown, concentration until your reaction is complete. Okay, you know the concentration of the stuff in the burette, you don't know the concentration of the stuff in your Erlenmeyer flask. And either one can be the acid or the base, it doesn't matter, but that's just normally we'll put the one that we know the concentration in our burette, in the unknown in the flask. And again, when the moles of our acid are stoichiometrically equal to our moles of base, then your titration has reached the equivalence point. That is when it's technically done, right? That's the goal. And then we use our indicator to see the color change, and this would occur at the endpoint. And again, we want the endpoint and the equivalence point to be the same. That would be ideal. All right, so like I was talking about a little bit, we have these things called titration curves, and this would be a plot of our pH versus the amount of added titrant. And the way that we would generate these would be through the use of a pH probe, which we are going to do in an upcoming lab. Like I was saying before, they kind of look like this, okay? And there's this inflection point in the curve, and that will signal represent the equivalence point of the titration. Before the equivalence point, so this is, here, I'll just kind of make this a graph. So this would be, our milliliters of stuff that's being added. In this case, it would be milliliters of hydroxide based on the way that I've drawn it. And then this would be pH over here. And before the inflection point, so all of this, that would be based on our excess acid. So our pH, the way that we would calculate that is based on the excess acid. And over here, we would base it on the excess base. Okay, and so we're going to look at how to do these calculations. But before the equivalence point, your solution, or your pH will be closer to the solution that's in your flask because the stuff in your flask is still in excess. After the equivalence point, your pH will be closer to the stuff that's in your burette because that will now be in excess. The pH of the equivalence point depends on the pH of the salt solution. So if we have a neutral salt like we've been talking about before, then the pH will be 7. So this would be for strong acid, strong base titrations. And this is what we're going to talk about today. In the next lecture, we're going to talk about these other ones, where the pH may be less than 7, and this would be in a weak base titration. And if the equivalence point would be greater than 7, and that would be in a weak acid titration. Okay, and again, beyond the equivalence point, our pH will resemble the pH of the solution in the burette. So here's an example. This is a strong base, strong acid titration. So we're starting with acid because if you look at our initial pH here, our initial pH is very, very low. It looks like our initial pH is 1, which means that we probably have 1 molar hydrochloric acid. So it's very, strong acid. That's how we calculate our initial pH. And as we continue to add base, right, because we're not adding very much base yet, our pH will still stay relatively similar to the initial pH of our hydrochloric acid because we still have excess moles of our hydrochloric acid. So some of the moles have been neutralized, but we still have a lot more left to go. At the inflection point here, right, at the equivalence point, our pH will equal exactly 7 because our moles of acid that we had exactly equal the moles of base that have been added, so they exactly neutralize each other, and the only thing in solution is water and our salt, which doesn't have any acidic or basic properties. And then after the equivalence point, right, now we have our neutral pH, so you can think about it essentially as being just water. After the equivalence point, if we continue to add base, then our pH will be very, very basic because we will have excess moles of our sodium hydroxide or, whatever hydroxide you're using. Okay. So you need to be able to do calculations in 4 different places. Okay. And we're going to go through and talk about each one of these. When you need to figure out the volume of base that you need to add to get to the equivalence point, you can do that by knowing, concentration and volume of your acid and the molarity of your base. Okay, we often want to know how much base we need to add to get to the equivalence point so that we can start to draw our curve, because you'll be asked to draw curves like these in this class and potentially in later classes. So you can use this formula, which should look very familiar to you because this is the same format as the dilution equation that we use. M1V1 equals M2V2. Well, now we have MAVA equals MBVB. So our molarity of our acid times our volume of our acid equals the molarity of the base times the volume of the base. And this can be a really quick and easy way to figure out the volume at the equivalence point. I want to caution you, though, This equation will only work if your reaction is a 1-to-1 ratio. So like if we have, hydrochloric acid plus sodium hydroxide that are reacting in a 1-to-1 ratio, we can use this formula. However, if you were using something like sulfuric acid and sodium hydroxide, they do not react in a 1-to-1 ratio. You cannot use this equation. So be very, very careful there. Okay, so now let's go through and talk about where we might figure out the pH. So initially, right, so at the very, very beginning, we haven't added any base. So we would just use our molarity of our acid to figure out the initial pH, because all this is right now is a strong acid problem. So we would take our concentration of our strong acid, which dissociates completely, so we can use that as our concentration of our hydronium ion concentration, and then we can take the negative log of that value to get the pH. The equivalence point is really easy in strong acid, strong base titrations because the pH is 7. You're done, right? Because our moles of our hydroxide are exactly going to cancel out our moles of our acid, so we have a neutral pH, so it's 7. The equivalence point is the trickiest calculation in the other types of titrations that we will cover. So it's really nice that in a strong acid, strong base titration, the pH is 7. And then the other one is before and after the equivalence point. Those are going to be the most work for the strong acid, strong base titrations. For both of these types of problems, you just need to figure out how many moles of either acid or base you have in excess, divide by the new total volume, and then calculate the pH from there. Okay, so it's still really going to be straightforward. You're just going to do a reaction ice table to figure out how many moles of each one you have, and then figure out which one is in excess. So we're going to go through a bunch of calculations today so you can see examples of all of these types of problems. So here we go. Titration practice problem number 1. So before you add any sodium hydroxide, what is the pH of 250.0 milliliters of 0.1 molar hydrochloric acid? So again, in this lecture, I'm going to always have the problem on its own slide and then the answer on the following slide. So if you would like to, you can pause and then pause and then work out the problem and then come back and watch the solution if you'd like to. Or you can simply watch through it so you can see how to do the problems. All right, here we go. So before any sodium hydroxide is added, what is the pH of 250 milliliters of 0.1 molar hydrochloric acid? Okay, so right now, we haven't added any sodium hydroxide. So we're just going to calculate the pH of the solution based on the concentration of the hydrochloric acid. So we don't even care how much hydrochloric acid we have, because if you'll recall, right, pH is just equal to the negative log of the concentration of H3O+. So we just need concentration, we don't need volume at all. So remember, strong acids dissociate completely in water, so this molarity of our hydrochloric acid, we can use that as the molarity of our hydronium ion. So we just take the negative log of that value, and that gets us our pH. All right, on to the next one. So now it says, what is the pH of the solution after 100 milliliters of 0.1 molar sodium hydroxide has been added to our hydrochloric acid? Okay, so now we have an acid-base reaction that's happening. We have base reacting with our acid, and as soon as you see that, you should think, I need to do an ice table. Okay, and specifically, I need to do an ice table in moles. Remember, anytime we're doing stoichiometry, right, or doing a reaction, our ice table needs to be in moles. When we're doing an equilibrium ice table, then we're going to do our calculations in molarity. But if we're doing a reaction, like we are now, it needs to be in moles. So our first step would be to take our volumes and our molarity and convert it into moles. So you can do it this way if you'd like. So I have it set up in a train track here. Or you can just do, moles is equal to liters times molarity. It's just the molarity equation that's been rearranged. Either way, whatever you want to do. So we get our moles of hydrochloric acid. That, because it dissociates completely, is going to be our moles of H+, or you can use moles of H3O+, whichever one you would like to use. And then we'll do the same thing with our sodium hydroxide. we'll get our moles of sodium hydroxide. And again, sodium hydroxide is a strong base, so it will dissociate completely in water, leaving us just with our hydroxide. So then we can write our reaction and make our ice table. So we're starting off with 0.0250 moles of our acid and 0.100 moles of our base. I've crossed out water here because it doesn't matter how much water we're making. We're doing this reaction in water. There's lots of water already. So if we add a teeny tiny more, a couple more moles of our water, nobody cares. All right, whoops. So this, because they are reacting on a 1-to-1 ratio, I'm not going to go through and figure out which one is limiting because it would be kind of redundant. We can just look and see which one's smaller. Remember, you can only do this if they are reacting in a 1-to-1 ratio. If they have any other numbers, any coefficients, you're going to need to go through and figure out which one is limiting. But here, since they're a 1-to-1 ratio, we'll just take the smaller one. So that's hydroxide in this case. So we'll subtract our value from the hydroxide from each one, and then we'll just add it straight down. So now we are left with moles of acid, and we don't have any hydroxide left. So this is telling us that we're still before the equivalence point. So if you look, if you think about our curve, right, our equivalence point pH is 7, and that would be when our moles of acid are equal to our moles of base. Remember that we started with hydrochloric acid, and right now we still have acid. That means that we are still before the equivalence point because we haven't added enough hydroxide to neutralize the acid that's in there. Okay, and so the way that we do this, we now have our moles of acid. We're just going to use that to calculate the concentration of the acid that is currently in our flask. Right? So remember, the way that the titration goes is that over time, we are adding volume of base, which means our volume is continually changing. So now we know our moles of our acid, but we need to calculate our new molarity by dividing it by the total volume. So we'll have our volume of our sodium hydroxide plus our initial volume of our acid, and we can calculate our concentration of our hydrogen ion. And then we can go through and we can take the negative log of that and figure out our pH. So as you can see, our pH here is fairly similar to our initial pH, right? It's gone up slightly because our concentration of our hydrogen ion has decreased, right? We have less acid in there because some of it has been neutralized by the base, but it's still very, very, very acidic. All right, let's try the next one. What is the pH of the solution after 250 milliliters of 0.1 molar sodium hydroxide has been added to 250 milliliters of 0.1 molar hydrochloric acid? Okay, looking at this, we have equal volumes and the same molarities. So just kind of just eyeballing it, we're going to have the same number of moles of each one, which means that this is an equivalence point problem. But let's go through the calculation anyway. So again, we recognize we have base being added to acid. So this is an acid-base reaction. The first thing we want to do is figure out how many moles of each one we have so we can put it in an ice table and figure out how much, what we have left over. So we'll go ahead, we'll calculate our moles of hydrochloric acid. This is the same as the previous problem. We haven't changed anything about our hydrochloric acid. We now have more sodium hydroxide that we've added, so we can go ahead and calculate that out. And now we can see, okay, our moles of acid are equal to our moles of base. So if we put that in our ice table, right, we don't have a limiting reagent because they have the same value. So if we subtract that out, we're going to get 0 for each one. We have no more acid, we have no more base, all we have is water. Okay, so this tells us that we are at the equivalence point. We have equal numbers of moles of strong acid and strong base that have reacted, and our anion here and our cation here do not have acidic and basic properties. Therefore, our pH is 7 at the equivalence point. All right, let's try another one. This one says, what is the pH of the solution after 300 milliliters of 0.1 molar sodium hydroxide has been added to 250 milliliters of 0.1 molar hydrochloric acid? All right, again, first thing we're always going to do is we recognize this is an acid-base reaction. We're going to figure out our number of moles, do our ice table, figure out what's left over. So there's our acid. Again, that's not changing. We'll calculate our new number of moles of sodium hydroxide, right, with our 300 milliliters. And then we'll go ahead and we'll put this in an ice table. So now when we're looking at these values, we see that the acid is lower in value, which means that's the one that we will subtract. So when we add them down, we now have leftover moles of base. This is telling us this is after the equivalence point, right? Because again, if we're thinking about this curve, right, pH was 7 here. Over on this side, we would have excess hydrochloric acid. Up here, we have excess sodium hydroxide. So this is telling us that this is after the equivalence point. We only have strong base. So that is what we will use to calculate our pH. So the first thing we need to do, figure out our concentration of hydroxide. Again, same way, you're going to put your moles of hydroxide that are left on the top divided by the total volume to get your molarity. And then remember, when you take the negative log of our hydroxide concentration, you're getting the POH, not the pH. This is a really common mistake in titration problems because you're so close to the end. You just type it in, that's the pH, and move on. So be careful. Make sure you look at what you're actually taking the negative log of. So once you have POH, you can just do 14 minus that value and get our pH. Again, this makes sense that this is, a very basic pH because all we have in solution is sodium hydroxide. If you had written this down as your pH, you should, recognize like, whoa, that's not right because I just saw the only thing I have left in solution is sodium hydroxide. It should not have a pH of 2.04. Clearly, I've done something wrong, right? And then go back and check your work and realize, okay, I've calculated POH instead of pH. Let me fix that. All right, I would like you to pause here and do a practice problem. Go ahead, calculate the pH of the solution that results from 10 milliliters of 0.15 molar sodium hydroxide being added to 50 milliliters of 0.25 molar nitric acid. Okay, once you're done, go ahead and unpause so you can see the solution. All right, let's go through this. So we're calculating the pH of this solution that results when we're adding our sodium hydroxide to our nitric acid. Again, this is an acid-base reaction. So our first thing we need to do is, figure out what's left in solution after the reaction happens. So let's figure out how many moles of each thing we have. So we'll do our base first. So we'll multiply our milliliters times our molarity. We'll get our moles. And then remember, it's a strong base, so it completely dissociates. So we can use that as our concentration of hydroxide. Then we'll do the same thing for our nitric acid, and we'll get our moles of nitric acid. Nitric acid is also a strong acid, so we can use that as our concentration of our hydrogen ion. So then we can write out our reaction. And so here, I've just written the net ionic equation, but if you wanted to, you could write out, okay, sodium hydroxide reacts with nitric acid to produce water and sodium nitrate. Okay, so again, they are reacting on a 1-to-1 ratio. All right, so we'll put our moles in our ice table, and then again, we're always going to subtract the one that's smaller. Okay, so we're going to subtract our base and then add straight down. So if you look at this, we have extra moles of acid. So we are going to base our calculation for our pH on the excess moles of acid. So we'll take our moles of acid, we'll divide by our total volume to figure out the concentration of the hydrogen ion, and then we can take the negative log of that value to find the pH of our solution. All right, one last problem, or one last type of problem for our strong acid, strong base titrations. We'll cover more titration-related problems in the next lecture, but one more for our strong acid, strong base titrations, and that is figuring out how much base you need to add to get to the equivalence point. So here we have 0.2 molar sodium hydroxide, and we're adding it to 40 milliliters of 0.25 molar nitric acid, and I want to know how much to get to the equivalence point. So again, we're going to make sure that these react on a 1-to-1 ratio. So I wrote the equation previously, but here it is again. So we have nitric acid reacting with sodium hydroxide to give you sodium nitrate and water. So they do react on a 1-to-1 ratio, so we can use that MAVA equals MBVB. I'm going to show you a different way to do it first through the dimensional analysis, the train tracks, and then I'll show you how to use that equation momentarily. So if you are going to use it doing dimensional analysis and not the other way, because the dimensional analysis will always work even if they react in a 2-to-1 ratio or a 3-to-2 ratio, something like that. This dimensional analysis way will always work. So you're going to start with the volume of whichever thing you know 2 pieces of information about. So like we know 40 milliliters and 0.25 molar nitric acid. So I'm going to start with the volume of my nitric acid. Then I'll use my molarity as a conversion factor to convert from liters of nitric acid to moles of nitric acid. And then we can use our ratio from the balanced chemical equation. We know that for every 1 mole of nitric acid, we will need 1 mole of sodium hydroxide. Okay, so we can use that to convert between moles of nitric acid to moles of sodium hydroxide. And then we can use the molarity of our sodium hydroxide to convert from moles of sodium hydroxide to liters of sodium hydroxide. So again, that's a way that, if you have something that's reacting not in a 1-to-1 ratio, then we can account for that ratio here from using the coefficients from the balanced chemical equation. But again, most of them that we will be using will react in a 1-to-1 ratio. So an easier way to do that is molarity of acid times volume of acid equals molarity of base times volume of base. So if we rearrange that to solve for the volume of base, right, because that's what we're looking for, we'll have our molarity and our volume of our acid on the top and the molarity of the base on the bottom. And then you can just plug values in and get your answer. Again, like I said, you can only use that when your acid and your base are reacting in a 1-to-1 ratio. Otherwise, you would need to use this top one. But again, it's not that many more steps. You just kind of lay it out a little bit differently. But they get you the same answer either way. So whichever way makes you more comfortable, do it that way. So on the examples that we've been doing, we were starting with a strong acid and then we were adding strong base. But you can do it the opposite way too. You can start with strong base and over time add strong acid. So like maybe you didn't know the concentration of your sodium hydroxide. So the way that you would do it is you would put your hydrochloric acid in your burette and you would put the sodium hydroxide down in the Erlenmeyer flask. And over time, you would continue to add your strong acid. So the way that you would recognize that this is a strong base titration instead of a strong acid titration is that your pH is starting very, very high, right? And it's going to start high and stay high until you reach the equivalence point, essentially. The equivalence point is still going to be at 7 when the moles of acid are equal to the moles of base. And then after the equivalence point, our pH will be very, very low because we will have excess acid that's been added past, our equivalence point. So this is just a reflection of the previous curve, right? The previous curve started low and ended high. Now we're starting high and ending low. You will do all of these calculations the exact same way. Our initial pH will just be based on the concentration of our strong base in water. So we'll look at that. We'll have our concentration of OH minus. We can find the POH and then, 14 minus our POH to get the pH. Here and here, you're going to do your reaction ice tables to figure out which thing is in excess, right? You've added, acid and base. You're going to figure out your number of moles, and then whichever one is in excess, you're going to divide by the total volume and find your pH from there. At the equivalence point, like I said, our pH is still equal to 7 because our moles of acid are exactly equal to our moles of base. So the only thing we have left in solution is water and our salt that doesn't have any acidic or basic properties. So here might be some data that you collect. Like if you started with our 0.1 molar sodium hydroxide, you are titrating it with 0.1 molar hydrochloric acid. Our pH starts high, ends low, but our equivalence point is at 7. Again, I'm including this because titration curves, they don't always increase from left to right. Sometimes they will decrease, like this one. It just depends on the type of titration that you're doing. So if you're starting with a strong base and over time you're adding acid, it will look like this. If you're starting with acid and over time you're adding base, then it will look like the other curve. Either way though, you're going to start very, very high and end very, very low, or you'll start very, very low and end very, very high. Both of these will have a pH exactly at 7. You will need to be able to recognize strong acid, strong base curves versus weak acids and weak base curves. So that's why I'm pointing out these key features. I'm going to talk about them more in the next lecture when we look at the differences between the two types of curves. All right, so that's the end of our slides for today. So today we talked about what titrations are and what they're used for and how they're an application of neutralization reactions. Today we've talked about strong acid, strong base titration curves, which are actually easier calculations than our weak base, weak acid titration curves. So I want you to get really good at these types of calculations and kind of understanding where you are in the curve before you go ahead and start the next lecture, because this would be foundational information that you need to understand before you start working on the weak acid and weak base titration curves. Make sure you are working through those lecture worksheets. There are lots of practice problems so that you get really, really good at doing these types of problems. Or go through and watch this lecture again and stop and work on each one of those example problems and make sure that you know how to do them and how to recognize where they are in the titration. As always, if you find yourself getting stuck or needing help, please reach out to me and I will be happy to help you. As always, keep working hard, learn lots of chemistry, and I will talk to you all next time.